In 2023, global agri-food systems emissions reached approximately 16.5 billion tons of carbon dioxide equivalent. Carbon dioxide equivalent is a standard unit used to measure the climate impact of different greenhouse gases on a single scale. Within this massive aggregate, the livestock sector acts as the dominant driver. Rearing animals for meat and dairy produces an emissions profile that matches or even exceeds the output of the entire global transportation sector. At the base of this footprint is a deep physiological divide between ruminant animals, like cattle and sheep, and monogastric animals, such as pigs and poultry. This chart shows the stark numerical tension between those two biological categories. Beef carries a median footprint of nearly 100 kilograms of emissions per kilogram of product, while poultry sits at just 10 kilograms. This 10-to-1 gap is hardwired into ruminant biology and geography, dictated by metabolic trade-offs and the immense spatial requirements of grazing. To find the true carbon cost of a diet, we have to look past the tailpipe model of industrial pollution and deconstruct the biological engines that drive animal agriculture. For ruminants, the primary driver of emissions is enteric fermentation. This biological process is an evolutionary necessity, allowing cattle to digest tough plant cellulose that humans and poultry cannot process. In the rumen, microbial enzymes ferment fibrous carbohydrates, producing volatile fatty acids. Volatile fatty acids are short-chain molecules that serve as the primary energy source for the animal, but their creation also releases metabolic hydrogen. This diagram illustrates the core thermodynamic constraint of that digestive process. If metabolic hydrogen is allowed to accumulate, it physically blocks the reoxidation of NADH. NADH is a crucial coenzyme that must be continuously recycled for fiber digestion to proceed. The digestive system avoids shutting down entirely thanks to methanogenic archaea, specifically a clade known as Methanobrevibacter gotchkalki. These are specialized, strictly anaerobic microorganisms that act as a biological exhaust system by consuming the excess hydrogen. Through a stoichiometric reaction, these microbes combine carbon dioxide with 4 hydrogen molecules to produce water and methane. This clears the hydrogen, but creates a high-energy waste product in the form of methane gas. This methane is expelled into the atmosphere, primarily through eructation, bleeding up to 12% of gross energy intake into the atmosphere. The ruminant itself operates as an inescapable methanogenic reactor. Evolutionary biology establishes a high baseline for greenhouse gas emissions that no amount of post-farm supply chain optimization can fully mitigate. The volume of methane produced relies heavily on diet, creating a counterintuitive dynamic. Intensive grain-fed feedlot systems often exhibit a lower enteric methane intensity than extensive pasture-based grass-fed systems. This split-screen diagram illustrates why. On the left, a high-fiber grass diet dictates a fermentation pathway that favors acetate production, which naturally releases excess hydrogen for the methanogens to consume. On the right, a high-starch grain diet shifts the fermentation toward propionate production. Propionate formation acts as a competitive sink, actively consuming metabolic hydrogen and starving the methanogens of their fuel source. As a result, feedlot cattle are biologically more efficient when we measure strictly by direct enteric methane emissions per kilogram of meat. However, achieving this reduction in direct emissions requires immense continuous inputs of industrially cultivated feed grain. Solving the biological methane problem at the animal level directly transfers the emissions burden off the farm entirely, relocating it into the fossil fuel-driven agricultural supply chain. Beyond the carbon cycle, the livestock sector shifts the global nitrogen cycle through the release of nitrous oxide. Nitrous oxide is a gas with a global warming potential 298 times greater than carbon dioxide. Anaerobic liquid manure lagoons act as perfect incubators, generating massive volumes of methane as the slurry decomposes without oxygen. Systems handling solid manure or depositing waste directly onto pasture operate differently, undergoing continuous cycles of aerobic and anoxic conditions based on moisture and soil density. In these environments, bacteria break down the waste through nitrification and denitrification. This is a leaky microbial process that constantly vents nitrous oxide as an intermediate byproduct into the atmosphere. To feed monogastric animals and grain-finished cattle, the agriculture industry relies on massive volumes of row crops, introducing a deep structural link to industrial chemistry. The immense yields of these feed crops depend entirely on synthetic nitrogen fertilizer, which is manufactured globally using the Haber-Bosch process. The vital hydrogen feedstock required for Haber-Bosch is derived almost exclusively through steam methane reforming. Steam methane reforming is an industrial reaction that extracts hydrogen directly from natural gas, making synthetic fertilizer effectively a fossil fuel derivative. The global agri-food system traps producers in a vicious cascade, forcing them to trade biological methane emissions for industrial nitrous oxide and permanent fossil fuel dependence. The final passive layer of climate forcing comes from the sheer physical footprint of meat production, measured as the carbon opportunity cost. This global map highlights the staggering spatial appropriation of agriculture, showing that up to 83% of all habitable agricultural land is dedicated exclusively to livestock and their feed crops. Despite consuming the vast majority of our agricultural space, animal products supply only 18% of global calories. Sustaining this immense footprint requires relentless expansion for pasture and feed cropland, serving as the primary driver of active deforestation in tropical rainforests. The demand is heavily fueled by the soy complex. Soybean meal operates as the premier high-density protein source for global poultry and pork operations. In active deforestation hotspots like Brazil's Matabiba region, soy production carries a land use change carbon debt 6 times higher than the national average. Land use change refers to the greenhouse gases released when natural ecosystems are converted into industrial agricultural zones. The carbon opportunity cost quantifies this destruction. It requires us to account not just for the greenhouse gases a farm actively emits, but the massive natural carbon sequestration it permanently prevents by occupying that land. The sheer physical space required to sustain animal agriculture constitutes a hidden climate liability that rivals its active, measurable emissions. Returning to our initial chart, we can deconstruct the order of magnitude gap between the footprints of poultry and beef. The first major block is the thermodynamic inevitability of enteric methane. On top sits the biogeochemical leakage of nitrous oxide, followed by fossil carbon embedded within synthetic fertilizers. Finally, the pillar is capped by the immense, invisible weight of the carbon opportunity cost. Monogastric animals bypass the enteric engine entirely and require vastly less land, locking their footprint at a strictly lower magnitude. Attempting to optimize within the ruminant system, like shifting from grass-fed to grain-fed models, often merely trades one form of radiative forcing for another. Achieving meaningful climate mitigation in agri-food systems demands a reckoning with these thermodynamic limits. Biology and geography, as much as logistics, dictate the true cost of our diet.